Okay, good morning to everyone. Ernie, we were listening to what? Phil Collins, Hand in Hand? Okay, thank you. This is week 11, I believe. And that means that we only have about 4 more weeks before we go into finals. And we are covering 6.5 and 6.6 this week, 7.1 and 7.2. We go up to the end of chapter 7 and into 8 before we have our exam in a couple more weeks for another major exam. We have a quiz on Friday, as usual, and I expect you to come in prior to the class and take it so it's done before we start. And so just a reminder, the quiz grades are part of your semester grade, and we have a quiz each Friday. You were working on 6.4 homework, and so questions on that, Bomaro?
Yeah, I have a question on 6.4.
Is it a particular problem in the book or one from the computer?
From the computer.
Okay. You want to share it with me?
Yeah.
Okay.
Find the square root of 0.01.
Square root of 0.01?
Yeah.
Okay, the answer to that can be done in a couple ways. The first is to realize that if you take 0.1 times 0.1, which is equal to 0.1, the square root will therefore be 0.1. Much in the same way that you know the square root of 4 is 2, because 2 times 2 is 4. Okay, that's probably the simplest way. The other on this is to understand that that's the square root of 1 times 10 to the minus 2. And then that's the square root of 1, the square root of 10 to the minus 2. And the argument there is to go ahead and understand that that's 1, and then this is 10 to the minus 2 to the 1/2 power. That was where we were talking about a square root being a fractional exponent. So that would give you 1 times 10 to the minus 1, which is that answer. Okay. Other questions on 6.4? Kim? Number 45 in the book on 6.4. Okay. Number what again? 45. Okay, we have the square root of 24. Ah, you're thinking of... You're supposed to approximate it to the nearest hundredth. But first, the square root does not mean take 1/2 of something. It's the 1/2 exponent. Okay? Now you're thinking of taking 1/2 of 12. As we come to the board on this part, what we want is something that's close to that when we square it. Now I note that 5 squared is 25. So I'm going to be very close to that. And so, without doing a calculator, about the best thing you could do is try to break this up, maybe make it a little bit smaller, or take a guess. So I can say something like, try 4.9 and square that and see what you get. Okay, so you would go ahead and actually, you're just trying to get to the nearest hundredth. This is the 10th at this point. And so, okay, gentlemen, if you stay with me. If you go ahead and do this, you would have 81 carrying the 8. So you have 44. Then you have a 36 and a 19. And so we have a 10, and then this becomes a 14 and a 2. So we're at 2401, and that's getting very close. No, I'm guessing what it might be. It's under 5. I note this. So I'm saying this is approximately 5 with a little bit taken off. So a 5 negative. So I try 4.9, and I get to 24.01. So I know it's smaller than 4.9. So 4.8. And then I try 4.89 or something like that. It is not a problem you want to do without a calculator, but that would be the process. And I try to watch what I'm selecting in there, hoping that I haven't managed to get something that requires a calculator. This one would demand a calculator to get it, unless you're going to go through that process of guessing, getting close, adjusting a little bit, checking again, and it gets tedious after a while. But it's going to be close to 5. And to the nearest tenth, 4.9, because I'm very, very close at 2401. Otherwise, when I square 4.9, I get 2401, which is very, very close to what I'm supposed to have. Other questions? That meant a little bit under. I sometimes used 5 plus, 5 negative, meaning a little bit less than 5. So it's not a sign. I'll just put approximately 5 if that will make things clearer. A little bit less than 5. So I tried 4.9. Any other questions there? Any other questions in 6.4? Okay. 6.5 is our next section. And as I come back center, we have applications in geometry. And this, again, is going to feel a little bit to you like deja vu, to the extent that you have seen much of this in the Math 10. So we're going to focus on that, order of operations and applications in geometry. Now the first thing, that order of operations that we had with integers, whole numbers, integers, fractions, doesn't change with decimals. So if you look at the kind of problem that's given here at the very beginning, the first example, page 452, that's pretty straightforward. You do the parentheses first, then you multiply, then you subtract. So the solution that is given, just to show you the process, notice that the parentheses was added. You had 7.4. Then you did a product getting 60.68. You did the final subtraction. So there's not too much there that's a mystery. If we have fractions and decimals, you always have the question of whether you want to make them all fractions or all decimals. And we occasionally do see problems like this. This is, again, the next page, 453, in which I have 6.09, and I'm not sure if there is one better way to do this. I think the obvious problem, if you'll remember, that 2/3 as a decimal is 0.66666 forever, so you're better off leaving it the way it is here. And I think my first reaction would be just to divide 3 into 609 because it goes evenly. So if I look at that from the standpoint of how I would approach it, and what I'm going to do is write that on the board first, Ernie. And it's just the idea of simplifying. Now what you're going to find down in the text is change it to a common fraction. But from a decimal point of view, you can see 3 going into there, 2.03. That's going to give you a 4.06 minus a 0.375, which you have memorized from your earlier work. 1/8 is 0.125, 3/8 is 0.375, and then you simply write this as 4060. I have a 375, and then whether you want to go ahead and do that with Austrian method or you want to borrow, up to you. But that's going to be a 5 there, and then we have an 8 here, and we have a 6 here, and we have a 3 here. So the 5 and 5 is 10. This is going to give you 16. That's going to give you a 10. Then that's going to give you a 4. This is a positive because in absolute value, this was the larger of the numbers. Kim? Memory? The question is, where did I get the 375? One of the ways I ask you to remember was that this is 125, and so if you remember that 1/8, this point 125, 3/8 is 3 times as large. So 3/8, 3 times 125 comes out 375 with the decimal. Now if you didn't see that, or you didn't remember that, you divide. It pays to have some things set in memory. Now that's not the way it was done in the text. Because this is, if I look at that now, that's 6 9/100 minus 3/8. And I'm not sure that looks like a thing I want to do very much with in terms of finding common denominators. Because this then becomes 2 over 3 times 609 over 100 minus 3/8. And there's some nice things to this to the extent this cancels, giving you a 50. This cancels, giving you 203, but I'm down to 203 over 50 minus 3/8. And now finding the common denominator for that is not good. So I'm not much impressed with trying to treat it as a total fraction. But as I come back to the document, Cameron, and we note that that's precisely what's carried out here, and I think that there's the step where I am right now with the 203 over 50 and the 3 over 8. You can see what happens here with the common denominator and eventually getting down to 737 over 200 and finally getting down to 3 and 1/37 over 200 or 3.685. No way. I mean, I can't see going through that when this is so effective. So 6 of one, half dozen of the other, but I can't really get too excited about what's done there in the solution with fractions. If we come back to the book for a moment, it's done in the next part. I can't get excited about that either, because this is doing what? Treating everything as decimals. And so there's that infamous 6's forever. And that's why you start getting these wiggly lines, meaning approximately equal. I wouldn't do that. If you come down here finally to this last statement, this is the one I just did in the board, and that's sort of an in-between. And I think that by far is the simplest method of doing it. And that's called method 3. You choose your own poison here. It's not really in every case the same way. There are a few problems where maybe fractions would work and a few problems where decimals will work, but maybe a mixture of the two is desirable. The procedure, and these are the ones I think are going to drive you nuts a little bit on the computerized homework, because a decision I suspect has been made by the person writing the solutions for you. And we'll say, well, it was to be done with method 1 or method 2 or method 3, and if you aren't putting in the right in-between steps, you aren't going to find acceptance. But as we look at to simplify numerical expressions, then you are going to, in step 1, write each decimal as a fraction. Or write each fraction as, let's see, each decimal is a fraction or each fraction is a decimal, or write each decimal number over 1 in fractional form. And that method 3 that we just did doesn't seem to be covered here in quite the way I'd like, to the extent that arguing that we write everything over 1. As I come back, coming out there for a moment, Ernie, I understand what he's saying. I'm just not sure that's as clear as I'd like. This is a good problem as we go back, just to focus on this, that is probably what I call some common sense. There would be nothing gained if 3 didn't go into 609 well. Otherwise, if 3 does not go into 609, I don't gain a thing. It's because 609 is divisible by 3 that it works. And if I had 2 over 5, then I would go to a decimal. I don't think it's going to lend itself to this is clearly what you're going to do each time. And I have a suspicion you're going to come back tomorrow and say, okay, I tried this problem and it didn't work well at all. If I look at the problems given, And I'm on page 463. Most of them are pretty straightforward. You can see the problems that are assigned here. I have them circled. And you have all decimals here. I don't see any reason for not just simplifying the parentheses and then multiplying. In 11, order of operations here, remember exponents are going to take priority. Then you have to be careful because after you've done that, you should do what in order? Division and multiplications in order given. So that division's done first, then the multiplication. Now, I'm not sure you're going to gain anything writing that with fractions. Down here in the 15th problem, this is very similar to what Bomaro was asking, and treat it in the same way because that's 81 times 10 to the minus 4, but treat everything with decimals. It's not until you get down to 19 that you have this mixture of fractions and decimals, and the only thing that makes this nice in this particular problem is that 85 is divisible by 5, so there's no way I'm going to take this and change it to 0.6. So I'll cancel first and then multiply. On number 23, again, notice how nicely it's been rigged. Caution here on 23. Don't cancel the 9 with the 1.8 until you have rewritten the mixed number as an improper fraction. But in looking at what's assigned on page 463 as we come off there, none of them are going to get into hot water. They've been rigged very nicely. And again, I don't want to push this process too far because, again, if I'm thinking of what this course is about, a pre-algebra, and I think in terms of trying to go from here into a 70, you just aren't going to do problems like this very often. So they're nice to the extent they're short-term. They force you to think about order of operations. They force you to deal with numbers other than whole numbers, other than integers, other than pure fractions. So they're nice in that way. But to say that you get done with these and you're going to be really well prepared for an algebra class, I don't think that holds true in that particular part of the problem set. So that's the first part. Now, the second part of this is referencing what I think you're going to find fairly typical formulas. So it's down to the formula chapter again. And every one of these you're familiar with. I'm on page 457. Of these three that are given here, we've worked with the area of a triangle before. We've worked with the area of a circle. And you have recently worked with the area of a trapezoid. That was what we'd done earlier. So that formula is not particularly new to you. As we look at a triangle, keep in mind that as I look at this particular green triangle, we have something different. We have restricted all of our work in the Math 10 to right triangles. So it's like taking just half that. Now, we need the altitude. So if this is your base, the altitude is to take the opposite vertex. These are called the vertices. There are three angles. So you take the angle opposite the base, and you take a line and drop it down like in a plumb bob so it meets here at 90 degrees. That is called the height. And that typically has to be given to you, or you might be able to use the Pythagorean theorem, 3, 4, 5, the 5, 12, 13 kind of relationships. Good old Pythagoras. Here's another one that we are familiar with. Now, finally, we get a payoff here for something I talked about in Math 10 that didn't go over all that well, never does the first time it's presented. But this is the volume of a cylinder. Now, the cylinder is shown over here on their side. But what I want you to note, they're using the Cavalieri principle. And that is, you take the area of the base times the height. So the area of the base times the height. And if we come off there for a moment, Ernie, and look back down at your classic rectangular what we called parallelepiped, okay, the box. But if we look at this box, the area of the base times the height gives you the classic formula, which is length times width times height. But again, it's the area of the base times the height. Same formula I'm using for a cylinder. Okay, so that is referred to as Cavalieri's principle. And just to comment that the rectangular parallelepiped, I've pronounced that way throughout my background, is actually given a different pronunciation because it came out of work in biology looking at crystal structures, and it's sometimes referred to as a parallelepiped. So a rectangular parallelepiped or a rectangular parallelepiped instead of piped, because epi and ped, the ped stands for like pedestal on the ground, and epi on the ground, and rectangular meaning at right angles. So Cavalieri's principle simply says that take the cross-sectional area multiplied by the height. And that works for a prism, okay, which is a triangular-based cylinder, if you will, that light goes through and gets refracted and goes into a rainbow of colors. And that's used in labs to show you how light is dispersed. Same argument. Find the area of the base, which would be a triangle, and then multiply by the height. Another formula, an old familiar one. Again, this is page 461, in which you have the volume of a sphere, 4/3, pi r cubed. So nothing's new there. As we look down at the bottom of 461, you've done these to the extreme, which means a composite shape. Here's a right triangle on a half circle, and you find the area of each one. Nothing particularly new there. So, thus far, there's nothing there that we haven't done, but now we get to go to a new one. A cone. This is called a right circular cone. Okay, this is on page 460. And you take the volume of a cylinder and divide it by 3. So if you have a cone, and I'm going to slide over, I need to come off there just for a moment so I can make the slide. Here is your cone. Now think of that being a cylinder. Okay, and I'm going to show you that in a moment coming off there. It's done very nice for you at the top of 460. And there it is. So think of the cylinder. And this one's a tough one to visualize. But if you take the volume of that cylinder, which is pi r squared, h, and then just divide it by 3, you have the volume of that cone inside. Okay, that has always been a difficult one for me to visualize and have that make sense to me. But that is the new one for you, the volume of a right circular cone. If we want to play that game, look at this pyramid whose base is a rectangle. Okay, so this is a very particular pyramid. Think of something like one of the buildings, is it the Transamerica building in San Francisco that has the shape, something like that? So you're going to have a square base, rectangular base. In this case, it happens to be square-based. But note, it's the same argument we had for the cone. Here is the volume of the related box, and you divide it by 3. So the point I'm making, if you understand that the pyramid and the right circular cone are just going to have 1/3 the volume of the related cylinder and box, you're in business. There isn't much new there. Here is the argument for page 459. And I'm not sure if you visually see it any better with that diagram. Okay, this reminds me a little bit of the Louvre in Paris, where you have out in front of the Louvre the idea of a pyramid. And for those of you who watched or saw the movie The Da Vinci Code, you saw a shape very similar to this. And the idea is that that's the pyramid based on a rectangular base and fitting in the box, and that the volume of the box would be length times width times height, and you just divide by 3. Now we refer to these as right circular cylinders, a right pyramid, in the sense that if you drop the altitude down, okay, if you drop a line from the top to the bottom, like a plumb line, that you're going to meet at right angles, and it's going to be in the center of that square or center of that rectangle where the diagonals meet. Not all pyramids and all cones are that way. Okay, they can be slid over. Think of a slinky. A slinky looks like a cylinder, but if you shove it over, okay, it becomes not a torus. You haven't brought it all around. You've left it stacked. Torus is like a donut. But if you take a slinky and then just pull one side over, you get that non-rectangular side. You get parallel sides, but it looks like a cylinder that's sort of gotten soft and started to collapse. All these problems on volumes are pretty darn straightforward. The biggest difficulty is you have to solve those problems pretty much without calculators or such. And here are some diagrams on page 467. So for example, you're to find the area here. I'm on 467, problem 31. And these are the problems I've selected. Page 467, problem number 51. Then 53 is your trapezoid. 55 is your circle. 57 is really a cylinder, just with a very small height. A quarter is a cylinder. So as we come off those, notice a change here. Didn't pick up this. You're using 3.14 per pi now instead of the 22 over 7. It's still not going to give you the exact answer. It's just an estimate. But as we come off there, then we have a composite. Okay, I have a composite on 65, which you have a half circle. You have the top of 67 coming off there, the top of the next page. Here's one that's a little bit different wrinkle. And you want the area of the shaded region. So you find the area of the square and subtract the area of the circle. It's a little different than what we've done before, but pretty straightforward. So I don't anticipate any problems with those two sets that I'm talking about so far. Now, some other things that are new to this unit. This textbook occasionally takes us into regions that are not as familiar to you out of Math 10. I'd like you to look at 467 at the top of the page, right side. Just some information, because this relates to physics more than anything else. I'm going to drop that down a little bit tighter. This is probably one of the most famous equations in physics in the history of mankind for somewhere around 5,000 years. It's Einstein's statement that the energy is equal to mc squared. Okay, and m is the mass. Does anybody know what c stands for? If you read there, it tells you the speed of light. Okay? And you have a problem. As I come over, using that formula, in which you are given some values. There's my formula. E equals mc squared. And you have a mass of 2.5 times 10 to the 6th. And the speed of light is given as 3 times 10 to the 8th. Okay? 10 to the 6th would be millions, right? So you have 300 million. And in terms of the speed here, I'm believing that's meters per second. I may not have, I'd have to check on that for the constant. Okay, so as we take a moment coming off there, the next one. This is out of Newton's work. And this has to do with the distance a particle travels, in which v is the velocity, t is the time, and a is the acceleration due to gravity, which is 32 feet per second. So if you think of velocity, okay, in terms of feet per second, and t is in seconds, and this is going to be 1/2 of 32, which is usually 16, you'll read this typically as vt plus 16t squared. And that assumes that you've started to throw something downward and it increases with an acceleration due to gravity. So if you throw something off the Empire State Building, for example, then there's that initial velocity multiplied by time plus what it accelerates. Well, if we look at that, and by the way, as we come off there, in the 47th problem, I'm a little bit bothered by the fact that these do not include the actual formula. There should be a D in front of that equals this. Up here there should have been E in front of it, because I would not accept your work without that E. But mostly it's a matter of substituting in. What I'm also bothered by, there are no indications of whether it's feet per second or what, and this appears clearly not to be a case with gravity, because this appears to be 10, which I assume, again, will be in meters per second. One last formula, and this is related to calculus. But both of these problems are related to simple interest. Okay, the simple interest formula that you had in the Math 10. And we come off there for a moment and come over to the statement. And it's calculating the balance in an account that is an earned interest, okay, compounded in times per year in t years. Interest rate is R, and use this formula to get what you have in the bank. I'll just tell you that this is e to the RT. Remember PERT, P times e to the RT, that's what that formula becomes. Now, without calculators, that formula is not something that you want to try, and I don't want to go into a calculator right now, so I've limited myself in the assignment just to the E equals mc squared, which I think is a reasonable choice. The explanations on those, get back to where that's given before all that work on area, etc. Here is the objective. It is evaluating expressions, and that's on page 456. I'm a little bit bothered by that in the sense that we evaluate expressions, but the expressions come from formulas that aren't themselves isolated to an expression. So that's the argument here in 456. But what I'm going to do is come up to the top, and here is the formula that was given. Okay, this is Vt plus 1/2 At squared, where this is distance. Now, the other thing I'm bothered by at this point, if I'm going to ask you to learn some of these formulas, I want them in a context that makes sense. And that is, we drop things in this, on the surface of this globe. You aren't dropping things on the surface of the moon. And so the gravity constant, that attraction, which causes things to fall down at a certain speed here, is 32 feet per second per second. If you're in the moon, it's a different value. But if you're going to play with the numbers, I would really like to see them explained in terms of the values that are used. Yes? Terminal velocity? Is there a limitation in how? Well, yes, and two ways. So the question, is there a limitation on how fast something can fall? You approach the speed of light, and the theory of relativity says as you approach the speed of light, the mass increases. And you never do get to the speed of light. You just approach to it. So in a sense, that's a limiting value in the theory that Einstein proposed. From a practical level, I think you're aware of there is a physical limitation. Because if something's orbiting around the Earth, and then, as has happened, things collide. And of course, that's been the big concern in the latest space shuttle that went up, because there was a lot of debris sitting out there because two satellites had collided. One of them was from the United States and one was from Russia, I believe. And they collided and left a lot of debris. In fact, if you look, there was a very nice effort, computer simulation showing where all the garbage is out in space. There's a lot of garbage. I'm sure somebody else looking from another planet, looking at us in another solar system, says, wow, they've got rings around the Earth. Sort of like ring around your collar. They've got rings going around that are just a bunch of debris that have nothing to do with asteroids and nothing to do with something that supposedly occurred in some cataclysmic explosion, the Big Bang Theory, and so we have these rings around Saturn and so on. We just have debris we've created. But what's the hope is that debris comes back and gets down out of orbit and falls back down to the Earth. What's the limitation on its speed? That point at which the friction is so great it burns up and disintegrates. So, if you are in non-vacuum and you are dealing with the atmosphere, there is enough friction that the particles simply burn up and annihilate themselves, so to speak, as an object before you reach the speed of light. So there are a couple limitations. And so to that extent, I don't want to try to make this a course in Newtonian physics or Einstein's theory of relativity, but these formulas do get involved. And when you go into an algebra class in particular, this formula that, again, is back in the document can, at the top of the page, is the one that we see there. Okay? So to that extent, we are evaluating an expression. As we come off that one, this is the substitution that we would have made for a problem in simple interest where you had an 8% interest and you were going to compound quarterly and you're going to do it for a half a year. And you want to know how much money would you have if you take $1. Well, you're going to, in essence, do this. And this isn't a bad problem because you can go ahead and get 1.02 and square that, and without having a calculator, get down to 1.0404. You have $1.04. But if you make the problem a little more realistic, and that is, as we come off there, that you have an interest rate not at 8%, but 5.75%, and you're going to do it 365 times a year, this is not a problem you want to do, even with a handheld calculator, unless it's programmable or you can take shortcuts. So, again, some common sense is involved here. Now, what I'd like to do, Ernie, is I'm just going to move over a little bit. I wanted to try to do something, and I don't know how successful I will be able to do this. But let's see if we can do something to... Okay, just a moment. I want to see what I have here. Helps if I spell it correctly. Okay, and... take just a moment to do what I want here, but I'd like to give you a realistic number for what's being involved here. And there we go. because a figure was given for c, and I'd like to see what it is. And if we look at the speed of light in miles per hour, just to give you some rather than feet per second, there is the speed of light in miles per hour. Okay, so that's going to be 670,616,629 miles per hour. And that's in the usual process. That's not the figure given to us. As I come down, and I gave you meters, and I should have given you kilometers, my apologies. But the speed of light in kilometers per hour, and I'm going to click on that, and let's pick this one up. I have, I didn't want to go there. Come off there for a moment, Ernie. I want to see if we can get a figure here, and they're giving it in miles per hour. I'm wanting it in kilometers per hour, and here we go. I think, yes. Okay, now we can come to this figure. This is some calculations that are provided off of a web page, but there's your last figure in kilometers per hour. Okay, so that is 1 with a comma, then 079. So let me try writing that because it's not reading very well there. So I have a 1, 079, then a 252, and then an 848.8 kilometers per hour. And so if I come to the board in that, this is going to be 369. So this is roughly 1 times 10 to the 9th kilometers per hour. And if you argue that that rounds off to the nearest, well, if I'm going to round off to this digit, then I would have 1.1 times 10 to the 9th. Yes, kilometers per hour. So in terms of the 300, I'm not sure where that figure is coming from. Let me come off there. I want to go back to the book here in a moment. Come back center, Ernie. But if I look at the figure given, let me come back to that. I just need to find, I lost the page number in that. I wanted to look at it again. And we have one more topic I need to go through. Okay, I want the formulas for that. We're evaluating an expression. Okay. Found it, 467. Okay, and so the figure given here on problem 45, where it's being given as 3 times 10 to the 8th. So if I look at what I have up here, okay, I think we can make a rough approximation. Again, the C was given as, let's come back to the book for a moment, 3 times 10 to the 8th. This was roughly 11 times 10 to the 8th. Okay, and that was in terms of kilometers. Okay, so if I think of that for a moment, in terms of 10 to the 8th, this is roughly 3 times what this is. Okay, and that's bothering me from the standpoint that if this is given correctly as kilometers per hour, and I'm going to look at another reference, and this is 3 times 10 to the 8th, that suggests meters versus kilometers, but then this would seem to me to be meters per second, and this as kilometers. No, not as kilometers. Okay. That's still, I'm getting 3 times as much. That's like in feet per second. And I guess that would be it. That if you think in terms of this being in meters, 3 feet is roughly 1 meter. And so if I divide this by 3, that would be the relationship, I think, of meters per second and feet per second as opposed to miles per second. So let's see if we can get a little bit better figure on here. Okay, they're giving some comparisons. I'm looking at this. We don't need to change anything, Ernie, but I don't like what I'm seeing there. I'm hoping that I can get a little better figure here in terms of what's provided. This is in miles per hour through the universe. Okay, light years. Okay. And what I was looking at here, I can't find a nice quick reference, so I'll take that as coming back to it in some point. There's some nice conversion figures given online, but I don't see them quickly. So I don't want to waste any more time with that, but it might be nice to come back. Tomorrow I'll try to have a better figure for there, because at the moment it's not tying together the way I'd like. Okay, there's one more topic in this set that relates to statistics. Okay, and I'm going to come back to a problem that's called a weighted mean. It's in the area of statistics. It's on page 455. Nope, not like the golden mean. A weighted mean. Now I'm going to write some numbers on the board for you for a moment. Let's leave that on the screen. But I want to look at just a 1, 2, 3, 4, and 5. Just these numbers as we go to the board. Now I have 5 numbers, and we're just going to add them together. So if I want to find x bar, which we talk about as the arithmetic mean, which you know as an average, as you talk about it, and that is the sum of the values divided by how many you have. Now that Greek symbol, and I didn't do justice to that Greek symbol, let me do it a little bit better. Okay, that is called sigma, and it means simply we're going to add up these numbers. So if I add up these numbers, and there's a very nice total here, from the standpoint that you get grouping by tens. So if you look at this, you have a 2 and a 3 is a 5, and this 5 makes 10, another 4 and 1 makes 10. That total is 15, so the summation of x is 15. And I have 5 numbers, so x bar is going to be 15 over the 5, which turns out to be 3, and sure enough, that is the middle number, and the middle number is referred to as what? The median. Now that's a median and the mean, and they happen to be equal to each other in my rigged example. Now what about a weighted mean? Now a weighted mean is sometimes written this way, in which I say that x bar is equal to the summation of the x times f over n, where I'm weighting each value by a frequency that it occurs. Okay, that's what we're going to talk about as a weighted mean. And so, for example, if I look at your grades, and I talk about your GPA, for every A you get 4 points. For every B, you get 3 points. For every C, you get 2 points. For a D, you get 1 point. That is referred to as a weighted average. So if I look at your GPA, looking at your grades, I have to weight them relative to what each grade is. So as I come back to the document cam, we have, as an illustration here, a little better scale than I just gave you, because at some institutions they do grade on the B+, C+, A, and so on. And so these are your actual distributions. So these are the weightings. So to that extent, the A- would be the same as a B+. And there's a nice little disclaimer over here on the side regarding that. The GPA is a weighted mean. Okay, and it tells you how many grade points you get for each of those grades. So the A is worth 4 points. And so if you had 3 units of A, you would get 12 grade points. So you calculate the GPA, total number of grade points over total credits. And this is how you get your GPA that is reported to the college and also puts you in academic probation if you go too low. Okay? And it's also a prerequisite to get into some schools that you have a GPA at a certain level. So if you want to go into graduate school, your GPA typically would be at 3.0 or higher as a typical kind of statement. So you're shown an example here on page 456, and I've selected one of these for your homework. Here's a case where the classic, so we come to the document cam, the Math 100, the English 101, Psych 101, Bio 101. Our equivalent of that is, in terms of the English, Psych, and Bio courses, would be Math 171 in terms of having something that would be university level, like your English 101 is, your Psych 101, and so on. These are the credits, and here were the grades for that. So you would, in essence, you have 4 credits, that's 4 units, if you will, and a 5-unit class, 3-unit class, 3-unit class, 4-unit class, semester units. So you multiply. For the A, 16 points. For this, you get 6 points. For the 3 at C+, that's 2.5 times the 3, and your 5 at a B+ is 5 times 3.5. So this should have been 4 times 4, that gives you 16. So down here, you see the assignments, and here are the numbers I was just referencing. Your 17.5, your 7.5, your 6, and your 16. So you have a total of 47 grade points with 15 units, 15 credits, if you will. And that gives you a 3.3, which is just under a B+. So you are at a solid B average. Question, Michael?
No.
Okay, and so this is technically a weighted mean. It's not quite the way we would do it in a stat course, but it's close enough. I'm comfortable with the terminology, and I will ask you to go ahead in the problems and do one problem where you look at a GPA, mostly because it's very practical for you as you look at your own GPA. So that pretty much covers the problems in this set. The one problem I was referencing a moment ago with the GPA is number 37, and it's done in a similar way. This is the problem that I've assigned. This is on page 466. Now, one of the things I've not done yet, and this is for those of you who are trying to do these without doing them on the computer, I have not placed this on the Math 20 week at a glance yet, and I just selected those problems this morning. So I have up and running 6.5, 6.6, 7.1, and 7.2 are all set up on the computer at this point. And then I will try to get these problems listed as part of the weeks at a glance as soon as I can. I can't do it right after this class, but that's how far I am in this. So for the week, my way I've set this up, I think I can bring this back up. Let's see if it allows me to on Course Compass. And I wanted to look at where I did the homework. But my point is, I think I've given you 2 days from today. Now, one of the things I'm going to encourage a little more diligence in, because if I give you too much slack here, I'm creating problems for you that I think work against you. I'm not expecting it to be completed by the next day, but about 2 days I think is reasonable, and you've got to find time to do that, and you can't play the game of catching up on the weekend and survive. So I'm not inclined to do that much more than an extra day, but I'm not going to be opening them up much beyond that. I think you've had a chance to get caught up, and so at this point you sort of live with where you are. You've got to get to the present and not stay in the past. And it sounds like a philosophical statement. But my point being, you've got to get up to where we are in terms of a daily basis, because if not, you're always playing catch-up and you won't be ready for an exam, and I'm very very concerned and also very proactive, trying to get it to the point where you do well in this next exam so that as many of you can survive this as possible going into an algebra. That's my goal. And you've got to pay your dues, and you have to make your effort to make that happen. I can encourage you by limiting how long I leave those problem sets open. So with that said, Ernie, we're down to about that.